Hello, welcome to today's class. In today's class, we will talk about problem formulation and state space. Actually, goal formulation and problem formulation are the first two steps performed by a agent which solves problem by search. So the agent needs to formulate the goal, then it needs to formulate the problem, and then it needs to find the solution by performing search. In today's class, we'll talk about problem formulation and we'll also talk about state space. And in the next class, we'll look at agent which solves problem by search. Now, problem formulation. A problem can be defined formally by using 5 components. The 5 components are the initial state, the description of possible actions that can be performed at a particular state, then description of what each action does, which is also called the transition model, and the goal test, which determines if a given state is a goal state, and a path cost function that assigns a numeric cost to each path. We will try to understand all these 5 components using an example. And the first example that we will take is finding a route given a map. So here we have a simplified road map of a part of Romania, and let's say that currently we are in Arad and our destination is Bucharest. So we now need to find a route from Arad to Bucharest, and it's the problem of route finding. And for this problem, let's see how we can formulate the problem. As you remember, we have 5 components in the problem formulation. So the first component is the initial state. So the initial state for this problem is that we are in the city Arad. So that's our initial state, and the actions, next component of problem formulation is actions. So what actions tells us is that for a particular state S, the function action S returns the set of actions that can be executed in S. So for a given state, what are the actions that can be executed in that state? If we take an example, if we are in the city Arad, then the possible actions that we can perform are we can go to Gerend, or we can go to Sibiu, or we can go to Timișoara. So these are the 3 actions that we can perform, and that's what is specified in the action component of the problem formulation. And these has to be specified for all possible state, not only for Arad, but for all possible state we have to specify the set of actions that can be performed. The next component is the transition model. So a transition model tells us what each action does. So if we consider a function result s comma a, so we have a function that takes as input the state and the action, the state s and the action a. So this function now will return the state, the new state that will be that will result from doing action A on state S. So we have a state S, and when in state S we perform an action A. On performing the action A, it will result in a new state, and that new state is what will be returned by this function, and that constitutes the transition model. When we specify this function for all possible states and for all possible actions, that would give us the transition model. One example here is that when we are in state in Arad, so this is the state we are in, and in this state we perform the action go to gerund. So result of performing this action go gerund while in state in Arad, the result, the new state is that we will be now in gerund. So like this we have to specify for all possible state and for all possible actions in that state, and then the complete specification will be our transition model. Next component in the problem formulation is the goal test. What the goal test do is it determines if a given state is a goal state or not. So now what is a goal state? In our case, our destination is Bucharest. So in this example, the agent's goal is the singleton set in Bucharest. So that's our goal. And now the goal test will determine if a given state is matching this state or not. The next component in problem formulation is the path cost. So now from our initial state in Arad to our destination, our goal in Bucharest, we can find out different path to go from Arad to Bucharest, and there may be, and we can associate cost with each of the different path. So that cost is assigned by the cost function. So path cost is a function that assigns a numeric cost to each path. In our example, the cost of a path may be the length of the path in kilometers. How many kilometers we have to travel. That may be the cost of a particular path. So I hope it's clear what the different components of a problem formulation mean from this example. We will look at few more examples. Now we will talk about state space. So what is a state space? The initial state, the actions that we can perform, and the transition model. Remember, transition model tells us what is the new state that will be resulted when we perform an action in a given state. So the actions, the transition model, and the initial state together implicitly define the state space of the problem. State space is the set of all states reachable from the initial state by a sequence of actions. So it's all the states that are reachable from the initial state. And the state space forms a directed network or graph in which the nodes are states. So in this graph, the nodes are the states, and the links between the nodes are the actions. And a path in the state space is a sequence of states connected by a sequence of actions. Again, let us try to understand state space using an example, and we will take the example of our vacuum cleaning robot. So for the vacuum cleaning robot, what is the total number of states? We know that In our example, we are considering only two rooms, room A and room B, and each of the room can be in two different states. So the room can either be clean or it can be dirty. And thus we have four possibilities for the room status. What are the four possibilities? The first possibility is that room A is clean, room B is also clean. The second possibility is that room A is clean but room B is dirty. And the third possibility is that room A is dirty and room B is clean. And the fourth possibility is both the rooms are dirty. So these are the four possibilities as far as room status is concerned. But now we also have a location of the robot, and the robot can be in either room A or in room B. So there are two possibilities for the robot location, and hence, so for each of these four possibilities that we had here, for the robot position we can again have two possibilities. So it may be that the room status is A clean, B clean, and the robot is in room A, or it may be that it's A clean, B clean, and robot is in room B. So for each of these four possibility, we can have two possibilities for the robot location, and hence the total number of states will be 4 into 2. So total number of possible states in the vacuum cleaning robot example will be 8. And if we consider a larger environment with n locations, then the total number of states will be n into 2 to the power n. So why will it be n into 2 to the power n? And that's because we have n rooms, and each of the room we have n rooms, and each of the room have two possible values. Hence the room status can be 2 to the power n. And since the robot can be in any of the n rooms, so for each of these 2 to the power n possibility, we have again n possibilities for the robot location. Hence it will be n into 2 to the power n. What if each room can be in 3 different states? Let's say clean, dirty, and semi-dirty. So 3 possible states for each room. Then what will be the total number of states then? In that, since each room can be in 3 different states, the possibility for the room status will be 3 to the power n, and location possibilities for the location is n, so total number of states will be n into 3 to the power n. Anyway, so these are the total number of states possible for the vacuum cleaning robot. And now if we try to see it pictorially, this is how it will look like. So we have the first state where the robot is in room A and both the rooms are dirty. The other possibility is both the rooms are dirty but the robot is in room B. Another possibility is only one of the room is dirty, so room B is dirty but the robot is in room A. And for the same room status where A is clean and B is dirty, we may have the robot in room B. Similarly, it may be that room A is dirty and room B is clean and the robot is in room A. And for the same room status where room A is dirty and room B is clean, the robot may be in room B. So that's another state. And another possibility is both the rooms are clean and robot is in room A, or both the rooms are clean and robot is in room B. So these are the 8 different states. And now if we try to show the actions from one state to the other, we get the state space. So this is the state space for the vacuum cleaning robot. So what we show in the state space is the transition model also. Because why transition model? Because let's consider this state where the robot is in room A and both the rooms are dirty. So now what are the different actions that can be performed? The robot can move to the right, and if the robot moves to the right, both the rooms will remain dirty, but the robot will be in room B. And this is the state. Both the rooms are dirty and robot is in room B. So when we are in this state and we perform going to the right direction, it will result in this state. Similarly, if we are in this state whether both the rooms are dirty and the robot is in room B, and now if we try to move to the left, that will make the robot move to room A, and that's what the state is. Both the rooms are dirty and robot is in room A. So when we are in this state and we perform the move left action, from this state we will go to this state. However, if we don't move to the left and instead perform the suck action, then what will happen is this dirt will get cleaned, and hence we will be in a state where room A is dirty, room B is clean, and our robot will be in room B. And that is the state for that scenario where room B is clean, room A is dirty, and the robot is in room B. So when we perform the suck action, we will transition from this state to this state, and that's what you will see for each of the state. So we are showing the state and we are showing what are the different possible actions in each state, and for each action we are showing the resulting state. So when we show the resulting state for a given action, for the move right in this state, the move right action will produce this new state, the suck action will produce this new state, move left will go to the same state, and when we show the new state for each action, that's your transition model. And we do it for all the possible states, 8 states. Why is it a loop here? It's a loop here because we are in room A and we are trying to move to the left. We cannot move and we cannot go to left. So if we try to go to left, we'll stay in the same room, and hence when both the rooms are dirty and we are in room A and we are trying to go to the left, we will stay in room A and both the rooms will remain dirty, and that's why for the move left we come back to the same state. Similarly, when we are in this state where we are in room B, and if we try to move right, when we are in room B, if we try to move right, we will stay in room B itself, and hence we have a loop here. Similarly, when the room is already clean and we try to perform a suck action, again the room will remain clean only, and hence we will go back to the same state. So that's why we see the loops in some of the states. So I hope this example clarifies what a state space is, and now we can also try to specify the problem formulation for the vacuum cleaning robot. So the problem formulation would look something like this. In total we have 8 states. The initial state, so any of these 8 states can be designated as the initial state. So the initial state can be that both the rooms are dirty and the robot is in room A, or initial state may be room A is dirty, room B is clean, and robot is in room B. So initial state may be any one of these 8 states. And what are the actions that can be performed at any given state? We can move right, we can move left, or we can suck. Then the transition model. What would be the transition model for this example? If you remember, the transition model tells us what would be the new state when we perform action on a given state. And in our example, the name of the actions itself is the name of the action itself tells us what the action will be performed. For example, move right, we will move to the right. Move left, we'll move to the left. Suck, we will suck the dirt. So the action performs as the name suggests, except that moving left in the leftmost square, moving right in the rightmost square, and sucking in a clean square have no effect. So that would be our transition model. And now the goal test. What is our goal state? Our goal is to have both the room clean. And now the goal test will check whether all the squares are clean or not. So that would be our goal test. And let's say and the path cost, let's say we are in, this is our initial state, and we have 2 goal states, and this is a goal state where both the rooms are clean. We have another goal state where again both the rooms are clean. So if we can reach any of these 2 states, then we'll say that we have reached our goal. And now starting in this state, there are different paths the agent may take. For example, the agent may come along this direction, then it may go along this direction, and then it may go along this direction, and it will reach the goal state. Or else the agent may go in this direction, then it may go in this direction, then it may go in this direction, again come back in this direction, again go this direction, and then come this direction. Or it may make a loop also. So there are different paths the agent may take to go from the initial state to the goal state. And now if we reach the goal in 3 steps, we can assign the cost of 1 to each step. So if we reach the goal in 3 steps, the total cost of the path will be 3. And if we take multiple steps, let's say 1, 2, 3, 4, 5, 6, then that path will cost 6. So different path may cost you different. So that's about the vacuum cleaning robot. Similarly, again we have the 8 puzzle game. Many of you may have played this game. So what we have here is a 3 by 3 square, and then we have these tiles 1, 2, 3, 4 up to 8. So 8 tiles, and then we have an empty tile. So now we can move this tile to the left, or we can move this tile 5 to the right. We can move this tile 2 downward, or we can move this tile 3 upward. The same thing we can view as the empty square is moving to the right, the empty square is moving to the left, the empty square is moving upward, and the empty square is moving downward. And by performing these actions, we want to reach a state where all the tiles are in sequential order. For example, 1, 2, 3, 4, 5, 6, 7, 8. So this is our goal state. So now a problem formulation for this problem, the 8 puzzle game problem, would be something like this. So a state description, how will you describe the state for this 8 puzzle game? We can specify a state by specifying the location of each of the 8 tiles. For example, in this case, tile number 1 is in square 9. Then tile number 2 is in square 2. Tile number 3 is in square 8. So like that we can specify the location of each of the 8 tiles and also the blank tile, and that specification will be your state description. The initial state, any state can be designated as the initial state. Here we may consider this is our initial state, but we may have another configuration of the tiles, and we may consider the other configuration as our starting state. Now what are the actions we can perform? As I said, you can think the actions being the empty tile moving to the left, moving to the right, empty moving to the left, empty moving to upwards, and empty moving downwards. So these are the actions that we can perform. The transition model, given a state and action, it will result in a resulting state. So if we are in this state and the tile moves to the right, what would be the new state? The new state will be 7, 2, 4, 5, 6 blank 8, 3, 1. So like that we can specify the new state for every possible action in each state, and that would constitute the transition model. And what would be the goal test? And this is our goal state, and the goal test will try to figure out whether a given state is same as this goal state or not, and how many steps we will take to find a solution to the problem. And if we consider each step, if we assign each step a cost of 1, and the cost of the solution would be how many steps we have taken to solve the problem. So that's your 8 puzzle game. Now 8 puzzle game, we have 9 squares. So the total number of possible states is 9 factorial. So why 9 factorial? Because the first square we can fill up in 9 different ways. Once the first square is being filled up, the second square we can fill it up in 8 different ways. And once both the first 2 squares have been filled up, the next square we can fill it up in 7 different ways. and hence the total number of ways in which we can fill up these 9 squares will be 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1, and that's your 9 factorial. So that's the total number of states we can have. But however, if you study n puzzle more, there are some mathematical proofs where it says that half of these n factorial states are not reachable. So you cannot reach half of these states from a given initial state. And hence, from a given initial state, the number of reachable state is actually half of n factorial, which is 181440. If you consider the 15 puzzle, so if you consider a 4 by 4 square instead of a 3 by 3 square, if you consider 4 by 4 square, that would be a 15 puzzle, and this 15 puzzle will have 1.3 trillion states. That's you can approximate it by 16 factorial. And similarly, if for a 5 by 5 board, which actually will be a 24 puzzle, will have around 10 to the power 25 states. Again, you can approximate it by taking 25 factorial. So as you can see, as we increase the size of, even for a very small board, just the 5 by 5 board, the total number of possible states are like 10 to the power 25, which is a very large number, and it takes a very long time for a computer to find a solution for a 5 by 5 board. Though we can find a solution for the 3 by 3 or the 4 by 4 relatively quickly, solving a 24 puzzle takes a long time. Next is the 8 queens problem. So 8 queens problem is about placing 8 queens on the chessboard such that none of the queen attack each other. And you know that queens can attack diagonally, or it can attack vertically, or it can attack horizontally. So if you consider this queen, if you consider this diagonal, it is not attacking any queen, and even on this diagonal it is not attacking any queen. Even vertically it is not attacking any queen, and horizontally also it's not attacking any queen. Similarly, this queen diagonally no, no, vertically no, horizontally no. So like that, you place the 8 queens in the board in such that none of the queens attack each other, and this is almost a solution for the 8 queens problem, except for the last queen. The last queen is not placed correctly because it is attacking the first queen diagonally, and hence this is not a solution for the 8 queens problem. In 8 queens problem, we have to place the 8 queens in such a way that none of them attack each other. Now a problem formulation for this problem is as follows. The states is that any arrangement of 0 to 8 queens on the board is a state. Initial state, there are 0 queens on the board. Actions, we add a queen to an empty square. Transition model, return the board with a queen added to the specified square. Goal test, 8 queens have to be on the board and none of them should attack each other. And path cost, the path cost is of no interest because only the final state counts. Anyway, we will be placing in only 8 times. So this is the problem formulation for the 8 queens problem. Um, so for all these problems that we have discussed, we can apply search to find out the solution of these problems. So we can find the solutions to this problem by applying search. Now there are other problems also which we can solve using search, and some of the real world problems that we can solve using search are listed here. For example, robot navigation. We want to move the robot in a room, so that problem also can be solved using search. Automatic assembly sequencing. So you want to assemble different parts together to create a complex object, and you want the robot to do this activity, and this problem of assembling different parts to create an object can also be solved by using search. The VLSI layout problem, where we need to position millions of components and connections on a chip, and we want to minimize the size of the chip. We also want to minimize the delay, circuit delay, and we want to minimize the stray capacitances, and we want to maximize manufacturing yield. So again, this is a real world problem which can be solved by using search technique. Then protein design, to design drugs which can cure diseases, can again be solved using search. Route finding, we already saw an example of finding a route in a given map, but not only finding the route in a given map, even for a travel by airline, where you have to connect different legs of the journey, or even military planning, all those can be solved using search technique. The Turing problem, where you need to start from a city X and then you need to visit all the cities, and then you need to come back to the original city. That problem also can be solved using search technique. And then traveling salesman problem, which is same as the Turing problem, but except that each city has to be visited only once. Again, this problem also can be solved using search techniques. And actually that's all for today's class.